So, here what we have is a piston and cylinder arrangement which looks like this. So, we are going to heat water in a piston cylinder arrangement. This process of heating water is slightly different from what we do, for example, at home, because at home what we would be doing is heating in an open container which is open to the atmosphere. So, there is air all around in that case, and so over there the liquid would be pure, but the vapor is in a mixture of air and the vapor would not be pure H2O. So, over here we have a different kind of arrangement where we have liquid water here covered by a piston. So, initially there is only water in this case. The piston has some mass and its weight is shown by W, and whatever process is going to happen here is happening against the same mass of the piston and weight. So, it is a constant pressure process, we know that already. It is a frictionless piston cylinder arrangement. So, the process is happening in this particular case at constant pressure. So, let us say we have pure water here at in this system at A, and let us say we start heating it. Let us say initially the water is at say 30 degrees centigrade and we heat it, and what we will be left with is, let us say, water at 40 degrees centigrade, and we continue to heat it, it becomes 50 degrees and so on. During this process the temperature of the water is increasing and the pressure is constant. What we expect is that the volume of the water will increase slightly because most substances when heated slightly expand. It is still water, it is still in liquid form, but we expect the specific volume to increase slightly. So, the volume at B is slightly more than the volume at A. The temperature at B is higher than the temperature at A, and they are both liquid water. If we continue to heat it more, we reach at some point the boiling point of water at this given pressure. If this pressure was say 1 atmosphere, then the boiling point would be 100 degrees or close to it. So, let us say at B we have now reached 100 degrees. So, we now have liquid water, all of which it is 100 degrees, it is ready to become vapor. So, if we give it some more heat, what happens is that this liquid starts to boil and become water vapor or steam. So, if we continue to heat it after a while, we have here liquid water, and on top of it we have some amount of steam. When water becomes vapor, its volume expands because it is now becoming into the gaseous phase. The molecules are no longer bound so tightly, they can move farther away. So, the steam occupies a much larger volume than the water for the same quantity of water becoming steam. So, we see that the steam is now starting to occupy some volume, and the volume between B and C has increased quite a bit. If I now give it some more heat still, what happens is that this water level starts to reduce because more and more of this water is becoming steam. So, let us say for example here I have this amount of liquid water left and everything else. So, I initially had this level, the volume has expanded quite a bit because a lot more has become steam. I continue to give it some more heat and all of this also evaporates or boils, and finally we are left with only steam over here. So, here we had only water, here also we had only water. So, these were pure water, and at some point of by water I mean these were pure liquid. Here I had a mixture of liquid and vapor, here I have a mixture of liquid and vapor still, here I have only vapor, and at this point all of it is already in vapor state. So, if I continue to give it some more heat, then the vapor becomes heated and becomes at higher temperature. I am still left with vapor which has a higher temperature than this. If I heat a gas, I know that it expands. So, here the volume is higher than this, the temperature is higher than this, which is essentially what I have. So, this is a process of boiling of pure water and only water, nothing else above it other than water, as I heat it from some temperature which is here to some temperature which is here. So, that is essentially what is happening in this case. I can now show this process on a TV diagram, temperature versus specific volume diagram. So, here the point A represents the state over here. It is completely liquid water, the temperature is low and the specific volume is low. The specific volume, as we know, is essentially V by M, which is essentially 1 by the density, 1 by rho. We know that at say close to 20 degrees centigrade, the density of water is roughly about 1000 kg per meter cube, which means the specific volume would be 1 by 1000 or 0.001 meter cube per kg. So, it is a small specific volume and the temperature is low. So, I have this point A over here. When I am heating it from A to B, all what is happening is that the water is becoming hot. So, the temperature is increasing to up to 100 degrees centigrade. In this process, the volume of this water is also increasing. But we know that when you heat a solid or a liquid, there is an increase in volume, but the increase in volume is not very large. So, we see that the temperature increases a lot, but the volume increases very little. So, the volume increases, for example, between here and here, whereas while the temperature increases between say here and here. So, the increase in temperature is this much from A to B, the increase in volume is only so much. So, it is a small increase in volume and large increase in temperature. So, between A and B, we see that this curve is very steep, it has a high slope. Then we reach the boiling point at B. So, once we have reached the boiling point, we know that any heat which we give is not what we call a sensible heating. So, we call it a sensible heating if the temperature increases, but once we reach the boiling point, we know that the temperature does not increase till all of the water has boiled. So, we would have what is called as latent heat instead. So, during the sensible heat period, we can use things, for example, as equations of this kind to find out the amount of heat transferred, but during the boiling point this does not work. So, we have, for example, the latent heat which is essentially being given, or if I have latent heat as heat in terms of per kg. So, this is the amount of heat which I need to give to convert all of the mass of liquid into vapor. So, what we see is that from the point B onwards, any heat I give is used in increasing the volume, because the temperature is not increasing, it is at the boiling point still. So, any heat I give is only used to convert liquid into vapor, and in that process to increase the volume. What we are noting is that this process, whatever we are talking of, is an isobaric process, it is a constant pressure process. So, any heat I give does not go to increase the pressure, because pressure is constant. Temperature also does not increase because it is at boiling point, so temperature is also constant. So, the energy I am giving is used in increasing the volume. So, from B to C I have an increase in volume. As I give more heat, more of this liquid becomes vapor. So, the volume increases even more, I get to some point D. So, what we see is that the temperature on this line BCDE is constant, but the specific volume is increasing because we are going to the right of this plot. We have more and more volume here, and finally we reach this point E, where all of this liquid has become into vapor. Once I reach this point E, as I continue to heat, I am now left with a single phase substance again with a vapor. If I heat a vapor, it becomes vapor at higher temperature. I am heating at constant pressure, so the pressure does not change. As it becomes higher temperature, its volume also increases, which is what we see. So, from E to F, what we see is that the temperature increases by this amount, the specific volume increases by this amount. The specific volume increase would be higher for the same temperature difference than on the liquid side here, and beyond this, if I continue to heat, I get a higher increase in volume and a higher temperature. So, that is essentially what I see as I go further and further to the right of this curve. So, this is the process of heating a pure liquid at constant pressure, which is what we are looking at over here. So, to summarize, water contained in a constant pressure device is heated slowly in the previous experiment there. The volume changes continuously. Temperature increases when water is either completely in liquid state or completely in vapor phase. During the phase change, temperature and pressure are remaining constant the heat transfer happens without a temperature change during the center portion when you have a mixture of liquid and vapor at constant pressure. So, what we have here are various curves of the kind we had. So, for example, this curve, the left hand side is not shown very clearly. So, let me just mark it here. So, this curve here shows what happens when you heat water at a pressure of 0.1 megapascal, which is essentially 1 bar, from a temperature of say this value to a temperature of say this value. This curve shows what happens when I heat water at say 1 megapascal, which is 10 bar. This shows the same thing at say 100 bar. So, as I heat it, it increases in temperature till it reaches a boiling point. Once it reaches a boiling point, the temperature and pressure are constant till all of the liquid becomes vapor. Once all of the liquid becomes vapor, the pressure and pressure is constant, I mean on isobar, but the temperature increases with the increase in specific volume. This is the same process when I have a different pressure. So, what we know is that if I have a liquid at say 1 bar and I heat it, it reaches some boiling point, after which boiling occurs. If I have a liquid which is at a higher pressure of say 2 bar, the molecules are being forced together by a higher pressure. So, I need to give it a lot more energy for them to get out of the liquid phase into the vapor phase, which means that the boiling point will increase, which is what is shown over here. So, at for example 0.1 megapascal, which is 1 bar, my boiling point is close to 100 degrees centigrade. We will see that it is not really 100. It is very close to 100 at 1 atmosphere. At 1 bar, it is a little less, because 1 bar is 10 power 5 pascal. 1 atmosphere is essentially 101, or let me put it this way, 1.01325 into 10 power 5 pascal. So, we have 1 atmosphere is this. So, an atmosphere is essentially slightly greater than a bar. So, we have 1 bar here, we would have 1 atmosphere which is somewhere like this, slightly above this, and that the boiling point would be close to 100 for pure water. If we go to about 10 bar, we see that the boiling point has increased over here. It is now above 400 Kelvin. At 100 bar, it is even higher. So, as I have higher and higher pressures, my boiling point increases. So, I have water boiling only at higher temperatures. So, now if I take the start of the boiling process and join all of those starts, for example, I take this point, I take this point, I take this point and join all of them, I get this black curve over here, which is essentially called the saturated liquid line. So, it differentiates what is water on the left hand side and the start of boiling, which means what is a mixture of water and vapor on the right hand side. So, here what I have is essentially liquid water. Here what I have is essentially a mixture of liquid and vapor. Similarly, if I take the end of boiling, the point where all of the water has just finished getting converted into steam, if I join all of these curves, I get this black curve over here, which we call as the saturated vapor line. So, the saturated vapor line distinguishes the liquid plus vapor region from the pure vapor region. So, we have liquid over here on the left, we have a mixture of liquid and vapor over here, and we have only vapor on the right. So, this entire curve is what we usually call as the liquid vapor dome, because it is liquid plus vapor, it is sort of shape of a dome. So, we call this as the liquid vapor dome. This liquid vapor dome has liquid and vapor inside it. It has liquid on the left hand side, it has vapor on the right hand side on this TV diagram. So, what I can also see is at low temperatures, the difference between the specific volume of pure liquid and pure vapor is large. It is this extent. This is the difference in specific volume. At higher pressures, this difference becomes smaller. At even higher pressures, it becomes even smaller. So, what I can see is, as I keep increasing the pressure, the difference between liquid and vapor volumes start becoming smaller and smaller, which means that at some point of time, this difference will become 0. which means that at some very high pressure, both the liquid and the vapor will have the same volume, and that point is what we call as the critical point, which I referred to also while looking at the compressibility charts. So, this is the critical point where this liquid line and this vapor line meet. So, that is the critical point. At the critical point, there is no difference between the liquid specific volume and the vapor specific volume. That is one thing. The second thing is, since in this process we are giving energy to go from this specific volume to this specific volume, and that energy is what we are calling as a latent heat, we see that the latent heat of evaporation varies as we go to higher pressures. So, at a low pressure this latent heat is large, at a higher pressure this latent heat is smaller, over here it is even smaller, and as we extrapolate this, what we see is when we get to the critical point, the latent heat becomes 0. And at the critical point, we can no longer distinguish whether it is a liquid or a vapor, because they are indistinguishable, there is no difference in some sense. And so, what we would generally say is, above it we would say at it we would say it is a fluid. We do not say whether it is a liquid or a vapor, because they are both the same. We cannot make out whether it is a liquid or a vapor, and we say it is some critical fluid, and at pressures above it we would call this substance as a supercritical fluid. At pressures below this, to the left we have liquid, to the right we have vapor, below we have liquid and vapor, here we have water at critical point, and above it we have supercritical water. There is also another interesting thing over here. If you look at this line, which is the vapor line, we see that this line is shallow. If you look at this line, we see that it is steep. So, on this curve is not symmetrical. One side of this curve is essentially steep, the other side is shallow. So, what we see is, as you increase the pressure, the effect of the pressure on the liquid volume, this line over here represents the liquid volume at the start of boiling. The effect of pressure on the liquid volume is not very high. As you increase the pressure, the liquid volume at the time of boiling does not change very significantly, because liquids are what we call as roughly incompressible. The volume does not change very much with pressure. In the case of this line, this represents the volume of a vapor or a gas. We know that the volumes of gases and vapors change a lot with pressure. As you increase the pressure, the volume of a vapor or gas becomes much smaller. Therefore, this line is shallow, because it shows that as you increase the pressure, the volume reduces. So, if I had a pressure here, this has some volume here. As I went to 10 times the pressure to this point, the volume reduced a lot. This was a reduction in volume as I went from a pressure of 0.1 megapascal to 1 megapascal at different boiling points. So, the temperature has gone up from here to here, but the volume change due to pressure is this much. If it was at the same temperature here, we would see that it would be even less. So, on the other hand, on this side, when we increase the pressure from here to here, the temperature went up and the volume increased, because there is an increase in temperature. So, what we see is that the effect of temperature is more on the liquid side than the effect of pressure, whereas on the vapor side the effect of pressure is higher than the effect of temperature. Because if I was at this point, the temperature is something, at this point the temperature is something else, because we have gone up in temperature, we have also gone up in pressure. Because of an increase in temperature, we would have expected the volume to be higher, but at the same time, because of the increase in pressure, we expect the volume to be lower, and the actual volume here is lower, which means that the effect of pressure is higher than the effect of temperature for this kind of a case. So, what we see is at low pressures, the latent heat of vaporization is high. At high pressures, the latent heat of vaporization is lower. At the critical pressure, the latent heat is 0. The corresponding temperature is what we call as a critical temperature, corresponding volume is what we call as critical volume. Above the critical pressure, both V and T increase with heating. So, if we just look at these regions on a plot like this, we have this liquid vapor dome. This is what we call as a saturated liquid line. This is what we call as a saturated vapor line. Under this dome, we have liquid and vapor. On the left of it, we have liquid. On the right of it, we have vapor. Because the vapor is above the saturation temperature, we also call it as superheated vapor. Above this temperature, we have what we call as supercritical fluid. This temperature is what we call as critical temperature. This isobar is what we call as the critical isobar, which passes through the critical point. And over here, it is all supercritical fluid. Far away from this dome on the right hand side, we have high specific volumes, and in this region we have high temperatures, and we are far away from here. And if we are far away from this dome, or if we are much beyond the critical temperature and at higher volumes, what we would call them is essentially as ideal gases. So, from the compressibility chart, we saw that if we are above twice the critical temperature, then, and if we are on a gaseous phase, then the gas behaves in an ideal fashion. Or what we saw is that if we are much below the critical pressure and at high temperatures, then the gases behave in an ideal fashion. So, far away from this dome, we have ideal gases on the right hand side. On the left hand side here, we have liquid, and beyond that we would have solids. So, that is essentially sort of a picture of these substances. So, we are going to stop here for today and continue in the next class. Thank you.